Let's look at another example for our sampling distribution of means. Now that we have kind of a clean slate here, just to kind of get at the key pieces that we're getting from a sampling distribution of means, because I know the simulation, there's a lot of information, goes to show a lot of background, and then in that last page, it just gets a little jumbled. But what this comes down to is basically three pieces. Central limit theorem, which, with the central limit theorem, you just want to refer to independence, randomization, and sample size. And in terms of work that you're going to show here, independence and randomization, you can just give automatic check marks when you're doing a problem with me. Just try to be careful of any wording that would break those, like if it's clearly not random or if the results are heavily dependent on each other. Want to be careful of that. Sample size, you'll always write something a little extra, and it will depend. On that last video, what we saw was that the population was normal. So maybe that'll be something that you write there as just evidence of why you passed the sample size condition, even if that sample is small. What we're going to see in this video is what happens when that population is not normally distributed. And with that, what we need to show is that the sample size that we're using is larger than or equal to 30. So in terms of our first step with these sampling distribution problems, we should be checking those three, and that's our evidence that we have a bell-shaped curve. Then your next step is going to be to define the parameters. And defining the parameters, we need to define what the mean is for our sampling distribution of means. And with that, you'll just copy the population mean. You'll need the standard deviation for our sampling distribution of means. And for standard deviation, you'll just take the population standard deviation divided by the square root of our sample size. Those three pieces there get us started for these problems. So let's talk about what happens when our population is not normally distributed. So we're collecting restaurant bills at a given restaurant, and what we have is a population mean of $32.40. So we have this population mean of $32.40. We have a population standard deviation of $8.16. And then we have this information that the data is heavily skewed to the left. So what we have for a picture here is something like this. So we could imagine for data here is there's this area of where we have bills that we mostly expect to happen, and that's what happens most of the time. So kind of on this higher end, maybe it's having 2 to 4 people go to the restaurant, which is kind of typical. But then what we have is this information in the left tail where we have some outliers or just some small values, like maybe that's just one person going in for dinner or even just a drink. Kind of these smaller bills that don't occur often, but they do happen. Explain why you cannot determine that a given bill will be at least $35. So we know what we expect for the mean, we know what we expect for the standard deviation, so why can't we find a probability? So with this, finding probability, we can only do this with a normal distribution. So if I wrote this notation right now in terms of a single bill being with the n and the 3240 and the 8.16, where this falls apart is me writing n right there. Because n says bell-shaped curve, which we do not have, because they tell us that it is heavily skewed. So if it was normally distributed, absolutely we could do this, but when it's skewed, we can't. We would need calculus to do it, and we're not doing calculus in this course. So with that, we can't find probabilities with skewed data. So, as compared to what we did in the last video, where our example started with a question in terms of probability for a single value, and we just applied what we learned in the normal distribution, we can't do that here because our population data is skewed. So, part B here, can you estimate the probability that the next 5 bills will average at least $35? So now what we're getting at is taking a sample size. So we're looking at this sample size of 5. And with that sample size, we want to talk about probability of the average. So now we're getting at sampling distribution of means. So to see whether or not we can estimate, this is where we're going to discuss the conditions, which means checking the central limit theorem. So do we have independence? Do we have randomization? Which, with those, just go ahead and go check. Check. Independence would be that each bill is independent of each other. Randomization is that it's a random sample. This actually isn't the best sample because they're in sequence of each other, but there might be some evidence that even if those bills are back to each other, the number of people and what they order is random enough. Then the last piece that we want to show is our sample size. So in the last video we could bypass even looking at the sample size by just saying the population is normal, but we do not have that here. So what we need to think about here is we have a sample size of 5. And in order to pass the sample size condition, that would need to be larger than or equal to 30. So that is too small. We're taking too small of a sample size. So we saw this in the simulation that we looked at, and we had skewed data, and when I took that sample size of 2, then the sampling distribution of means was also skewed. Kind of mimicked what was happening in the population, and that wasn't good. So that's where the sample size condition came from. So when we get to the sample size condition here, we're going to fail. So since we fail our central limit theorem, we cannot estimate that probability. No, we cannot. Because again, even if it's a sampling distribution of means, it would be skewed. So we would get stuck with a skewed distribution again. Part C, if we take the average, so again looking at the mean, and of the next 50 bills, would all the conditions be met? Yes, because we'd have independence, that would stay the same, randomization would stay the same, and then to show our work for the sample size condition, now our sample size is 50, which is larger than or equal to 30. And now we have a large enough sample size, so we pass the central limit theorem, so now we can find probabilities. So with that, let's build a sampling distribution of means around this sample size of 50. So we know we have a normal distribution, so now we have a bell-shaped curve because we passed the 3 conditions, and we're taking a large enough sample size so that it, like we saw in the video of the simulation, when the sample size was larger, then it became a normal curve for the sampling distribution. So the parameters, we need our mean, which we just copy our population mean that we had initially, which was the 3240. For standard deviation, we're going to take the population standard deviation of 8.16 over the square root of 50. And I skipped this in the last video, but just to show you how to plug this into a calculator, I'm going to go to the Desmos scientific calculator here. It appears pretty much the same as the GeoGebra scientific calculator. Typically, the Desmos is working better on my computer for some reason, so if you're having issues with the GeoGebra, maybe switch over to the Desmos one. But what you'll want to do is create your fraction. So there's this a over b button here, and we'll have 8.16 in the numerator, and then in the denominator we'll have a square root of 50. So just so you can see how it should be typed in, and that'll be a 1.153, nope, that'll be a 4 there, is how that'll round up. So 9 rounds that up to 10, which carries a 1 over. So, standard deviation is going to be 1.154. So our model for this distribution of means is normally distributed, since we passed the central limit theorem, centered at 3240, standard deviation 1.154. So to get a picture going for what this will look like, just to get a sketch, and we can see our number line. So we expect 3240 for the average of these 50 bills, and then bumping up by 1.154, and I'm going to round this just a little bit since we just need to see generally where these numbers are landing. Let's see, 34.71, 31.25, and $30.09. Alright, so we found our parameters, the mean, standard deviation. We defined the model, as we did up above there, and then drawing and labeling graph. So how likely is it? So in terms of finding a probability, the next 50 bills, so we have our sample size average, so we know we're using our sampling distribution of means, at least 35. So from our picture up above here, actually you can see 35 isn't even listed here. Seems like 35 isn't that far off from 3240, but in terms of averaging 50 bills, so averaging this large number of bills, we expect to be really close to 3240. So even being just at 35 is pretty far away, and at least means we're taking an area to the right. So we're looking for the probability of x being more than or equal to 35. And now we'll go over to GeoGebra. So in GeoGebra, I have my mean of 3240, standard deviation 1.154, and we're going more than or equal to 35, and that's going to be a 0.0047. Sorry, pause there because that didn't match up with my answer sheet. It was looking for an error, and it's the mean there. It says 32. Let's get that 0.4, and then you can see that probability changes a lot, which I'm going to leave this in here because that's a great lesson on make sure everything's typed in correctly, because leaving off some decimals, make sure you're going to 4 decimal places when you can really change the probability. So 0.0121 is our answer there. So we're going to have, there is a 1.21% chance the next 50 bills have an average of at least $35. All right, so that's our sampling distribution of means. In terms of recognizing whether or not a question is dealing with a sampling distribution of means, the key is that they're going to give you the population mean and population standard deviation. Maybe they'll tell you that that population is normally distributed. Maybe they'll describe that it's skewed. Maybe they won't say anything about the shape of the population data. Just keep in mind that if they say it's normally distributed, our sample size condition changes. Otherwise, the sample size should always be larger than or equal to 30. And then in terms of the types of questions that they can ask about probability, they could ask for cutoff values like our percentile question. But the idea is in the wording somewhere, they should talk about average or mean from a certain sample size. So this idea in terms of probability or cutoffs regarding averages and means from a certain sample size, that's going to require our sampling distribution. So like in part E there, they talk about the sample size of 50 and want to know how the average of those 50 will behave. That's a sampling distribution of means question. Alright, so that will do it for our sampling distributions of means.